Well, as you can see in this problem, we are dropping a pendulum bob, and it's going to swing. Up here at the top, it of course has potential energy. Down here at the bottom, it is going to have kinetic energy only. It doesn't have any potential energy down here. We're going to call the lowest part in the swing h equals 0. And of course, we would like to know what is the velocity at point C. How fast is it going? We are told the length of the pendulum. It's 75 centimeters. And that's all we know, except that we're dropping it from perpendicular. So the height of the bob up here at A is the same as the length of the pendulum. So once again, the law of conservation of energy writes the equation for us. The potential energy at the top equals the kinetic energy at the bottom. Of course, potential energy is mgh. Kinetic energy is 1/2 mv squared. The bob doesn't change mass as it swings, so the mass cancels out. We have that on both sides of the equation. And we can very quickly solve for v. Let's see, we're going to multiply both sides by 2, and we're going to take the square root right away. If I turn that equation around, plug in some numbers. Gravity is 9.8. Height was 0.75 meters. Let's see, we find out that is 3.83 meters per second. Not too difficult. Let's look at it again, but we're going to swing up to a higher angle. In the second part of this problem, we'd like to find out how fast it's going as it swings up to a higher height. I believe we're told this angle is 37 degrees. And so it's not at the lowest point anymore. So over here at point B, it's going to have both potential and kinetic energy. It is moving at that point. And once again, we of course would like to know what is the velocity. That'll be tangent to the curve. V at B is question mark. That's what we'd like to know. In order to do a problem like this, we're going to need to look at the geometry. What is going on here? We know that the length of the pendulum from the center, the pivot point, to the center of mass is 0.75 meters. What we don't know is how high is it off of the ground. But we can use this angle to figure it out. What we like to do here, this is very common, we're going to construct a perpendicular, a line that's horizontal to the ground. This is now a right triangle, 90 degrees, and the height from here to here, from above the ground, we're going to call that h. Okay? So if you look at that, what the distance from here to the center of the bob when it was at point C before, that's also the length of the bob. The distance from here to here is L minus h. Think about this. This is h right here. If I were to bring it over here, that's h. The distance from here to here is L. So L minus h is this side right here of a right triangle. And we're going to use that in just a moment here to figure out h. But let's start with our conservation of energy equation. We're going to say this: the potential energy at point A is equal to the potential energy at point B plus the kinetic energy at point B. Once again, let's substitute some things that we know. mgh. Now, careful, this is the height at A. That is 0.75 meters. We have here the potential energy at B. That's that new height that we're going to need to figure out. And 1/2 mv squared. And that's actually what we're looking for V. Let's start off with the simple stuff. Of course, mass cancels out. Once again, we have mass in every single term. And I'm looking for velocity. So I'm going to go ahead and do this. Let's bring all the potential energy terms over here and pull the G out of the equation. So HA minus HB. There's that. I'm going to go ahead and multiply both sides by 2. So we have velocity squared on that side all by itself. But of course we have a problem here. We know the height at A, we do not know the height at B. So I need to go off to the side just a little bit. Let's take a look at this triangle that we have here. Actually, I'll write it right in this space here. That should work out nicely. The trig function that relates the adjacent side and the hypotenuse is cosine. So I might write cosine of the angle is adjacent, that's L minus H, divided by the hypotenuse, which is L. And if I rearrange that equation, we find out that H is L minus L cosine theta. And that's, I should probably be clear here, that's the height at B. That's the H that we're talking about there. The height at B is L minus L cosine theta. So let's go back to our equation here and substitute some of those ideas. At this point, I'm going to turn it around just to save some space here. This is VB squared. Let's start rewriting this. This is 2 times G. The height at A, you might recall, is it's the same as the length. So I'm going to write L, that's the height at A. We just found out that the height at B is L minus L cosine theta. So let's see here. This was minus. I have to be careful. I have to be very careful here because it's minus that height. So it's minus L plus L cosine theta. And all of that equals the velocity squared. Let's do some simplification here. Of course, we still have 2 times G out front. Inside we have L minus L plus L cosine theta. So that just becomes L cosine theta. And I believe then I can go ahead and actually get rid of the parentheses because there's no more addition in there. And there's our final equation. I just need to take the square root of both sides and we have V all by itself. Let's plug in some numbers and see what we have. And as you see there, we find 3.43 meters per second, which is a little bit slower because we found the velocity over here at C was 3.83. And that makes sense. As it goes back up, it begins to slow down. And there we have it. The key things in this one to remember is how to deal with this triangle to find the height.